Materials with cubic symmetry are quite common. Simple examples are silicon, iron, nickel. Many materials have cubic symmetry, and this is something that you see in X-ray diffraction patterns for these types of materials. And I'd like to go through the implications of cubic symmetry on the linear elastic material properties for such materials. So first of all, what do I mean by cubic symmetry? So this is a material that has symmetry transformations that include all the orthotropic transformations, so 3 reflective planes of symmetry, but it also includes rotational symmetry about any of the orthotropic axes, and rotational symmetry in increments of 90 degrees. So we have, in addition to the reflective planes, we have these 90-degree rotational symmetry elements. Just as an example, when we say 90 degrees rotational symmetry elements, maybe let's think about a 90-degree rotation about the 2-axis. So if we had set up a coordinate frame 1, 2, 3, again, this frame will be set up so that each direction is orthogonal to a reflective plane of symmetry. And then 90-degree rotation about the 2-axis would generate a new frame of reference, 1 star, 2 star, 3 star, where 1 star was pointing in the downward direction relative to the drawing there, and the 3 star direction ends up pointing out of the plane, so it ends up being parallel to the 1 direction. And the 2 direction is the same as the 2 star direction. Now, material symmetry tells us that the components computed in the star basis, where the star basis is related to the unstarred basis through any symmetry element of the material, so either reflection about or with respect to the 3 orthotropic planes, or 90-degree rotation about any of the orthotropic axes. And so if we compute the components in the star basis, they're equal to the components in the unstarred basis. So that's what we mean by material symmetry. And let's just look at the case where, for instance, we look at the 2, 2, 1, 1 component. So I'll set I equal to 2, J to 2, K to 1, and L to 1. So if I do that, then I'm going to find out that C2211, where all of this term here on the left-hand side is computed with respect to the star basis elements, and the C2211 here is computed with unstarred basis. Now, if I just look at my diagram here, I note that 2 star is equal to 2, and I'll note that 1 star is equal to minus 3. So what that is going to end up telling me is that C2233 in the unstarred basis is equal to C2211 in the unstarred basis. So this is an interrelationship between elastic constants that has to be preserved. So what this is going to tell me, if I start walking my way through the modulus tensor in the 6x6 form, first of all, I'm going to find out that all the diagonal elements have to be equal to each other. So that's one thing that I'm going to find out. And remember, I'm starting with the orthotropic case. So in the orthotropic case, we had 3 different numbers along the diagonal in the upper 3x3 block. Using these rotational symmetries, we find out that those 3 numbers actually have to be equal to each other. We also find out that the off-diagonal elements have to be equal to each other. In fact, that's what we've just proved here, or started to prove here. And for instance, we've shown that C2233 is equal to C2211. So C2211 is over here, and then by symmetry, it's equal to this guy here. So we've shown that these 2 off-diagonal terms above the diagonal are equal to 0. And you can continue in that way, and you can show that that upper element is also taking on the same value. If you work your way through the rest of it, you'll find out that the 3 diagonal elements in the orthotropic case in the lower right 3x3 block are all equal to each other. So we end up now in this particular case with just 3 elastic constants. Alpha, mu, and lambda are typical symbols used to express those, but just to be clear, alpha here is C1111, lambda is C1122, and mu here is C1212. And so there are really only 3 unique elastic constants for cubic materials. If you want, you can also express the elastic moduli in a coordinate-free form. This form up here is set up where the coordinate axes are orthogonal to the reflective planes of symmetry. But if you want a coordinate-free relationship, you can write it as follows. You can write it as lambda identity, outer product identity, plus 2 mu times the symmetric identity, plus alpha minus lambda minus 2 mu times A outer product with A outer product A, again for B, and again for C, where A, B, and C are vectors that I'm going to call the cubic directions. They're the ones; those are the vectors that are orthogonal to the reflective planes of symmetry. But they're not necessarily E1, E2, E3 now in this general expression that I have written here.